Okay, well, at the opening of this particular lecture, we have one more chapter that I would like to accomplish this semester. um, would have been nice if we could have gone even further, but some of the early stuff took forever. But anyway, chapter 7 is on work and kinetic energy and power. Don't forget power. um, it has to do with some of the various forms in which energy is related to movement. And the next chapter, which I'm hoping to get just a little bit of, has to do with potential energy, which is the energy that an object has because of its, say, its condition or its state. So kinetic energy has to do with how much energy something has when it's in motion. Potential energy has to do with the kind of energy that something has when it's sitting still, because it's a certain distance off the ground, for instance. Anyway, what we've got here in this chapter is between work and kinetic energy and power is that some of the basic concepts related to motion and they're related to each other can lead us to what's known as the work energy theorem. And that's later in the chapter. And that will often provide an easier way to find out information about objects that are in motion based on the forces acting on them based on its motion, or by finding out its motion based on the forces acting on it, one or the other. But that's still in the future. So let's actually get right into work. Work is a type of energy. It's a type of energy that can cause movement or displacement in something. And it's measured in energy units. Okay, so work and energy are closely related concepts. In fact, work is a form of energy. Work is done when a force applied to an object causes the object to move. In other words, when the force applied to an object causes a displacement in the object. Work varies as a function of displacement. So the farther the object moves, the more work has been done. And it also varies with the amount of force that's being applied to the object. Displacement can be along more than one path. So in the simplest cases, we'll be treating displacement along one direction. Like, for instance, I push on this pen and it moves in one direction. But the force could have caused displacement in more than one direction, X, Y, and maybe even Z as well. The simple equation for force, the one that's used a lot because it only involves magnitudes and not directions, is that work equals force times distance. W equals FD. That's a very common equation in physics. But if you want to go into more detail and in more fundamental aspects of it, you can look at an infinitesimally, why can't I say it? Infinitesimally small increment of work, which we can call dW, being done by force, causing an infinitesimally small displacement, which we'll call dr. R just being an expression of position as a dot product. Okay, so dW, that is this infinitesimally small increment of work, is equal to the force as a vector as a dot product with the infinitesimally small movement that force causes. And in calculating that, we can calculate that as the magnitude of the force times the magnitude of the displacement times the cosine of the angle between, theta is the angle between the force and the displacement. Okay, so theta is the angle between force and displacement. In a lot of cases, the force and displacement are parallel to each other. Like if I push on this pen, I'm pushing in this direction, and the pen is moving in this direction. And so the force and the displacement are parallel to each other. And in that case, cosine would be 0, or sorry, the angle would be 0, and the cosine of 0 is 1. So in other words, if the force and the displacement are parallel to each other, then dW is just magnitude of the force times the magnitude of the displacement, which is kind of just another way of saying W equals FD. Because D being distance or displacement. So if you've got a complicated situation in which the force or displacement are being exerted in various directions, then you would just have to basically add up all the contributions from the various displacement along the path of movement to get total work. And that is leading up to what you might suspect to be an integral, and indeed it is. The work done by a force is the integral of the force with respect to displacement along the path of movement. That's basically what was just said above, only said more mathematically here. When you're adding up a whole series of tiny little items one after another, that's basically what an integral is. Only in an integral, theoretically, the tiny little items are infinitely small. Okay, so work in moving something from point A to point B would be equal to the integral between A and B of the force times the tiny little increment of displacement. If the path is from A to B along a curved line, then the total work going from A to B is really just a summation of all of these tiny little increments going from here all the way to there. So tiny little increment there, all the way through up to there. And you have a force that causes the movement in a certain direction. And so when you add up all of those forces and the dot product of the force and the displacement, you get the total work. Okay, the work done over a displacement by a force is a product of one of the components acting parallel to the other. And the order doesn't matter because it's a dot product. All right, moving on. The magnitude of the force times the cosine of theta. The angle is, again, is just the angle between the force and the displacement. That's a component of the force in that direction. Each component of the force could be positive or negative or 0, depending on what the angle is. And so because of that, the work can be positive, negative, or 0, depending on several things. If the work is done in the same direction as displacement, then work is positive. If the work is done in the opposite direction of compared to displacement, then the work is negative. And if the work is done perpendicular to the direction of displacement, then the work is 0. And that is going to be important in a lot of cases because, for instance, as I push this pen across the paper, my finger pushing on the pen is not the only force. There's also the force of gravity. So you might think, oh, wait a minute, force times distance. Okay, I'm taking the force of my finger pushing it times the distance it moves. And that might not be all of the work because you've also got the force of gravity pulling down on the pen, creating its weight. And weight is a force also, as is the normal force pushing up on the pen. And so you might think, wait a minute, don't we have to include those forces in the work of that's done on the pen? Well, the answer is no, because those forces, the force of the weight pulling down on the pen and the normal force of the paper pushing back up on the pen are going up and down while the pen is moving horizontally. So in other words, the force is perpendicular to the direction of displacement, and therefore the work is zero. That is, the work done by gravity and the work done by the normal force are zero. So the only work or the only force that you have to be concerned with in moving the pen to the side like that is my finger pushing on it, because that's the only force that is not perpendicular to the direction of movement. In this case, the force is in the same direction as the movement, and so the work would be positive. As far as the units of work are concerned, as I mentioned before, work is a form of energy, and so we express work normally in the same units as energy. And work is equal to force times distance. Then you would expect the units in the SI system to be the units of force times the units of distance. The unit of force in the SI system, of course, is newtons, and the unit of distance would be meters. And so the SI unit for work or energy in the SI system should be Newton meters. Or remember what a Newton is. A Newton is a kilogram meter per second squared. If you take that and multiply by meters, you get kilogram meter squared per second squared. And because they had some famous physicists who hadn't had anything named after them yet, they decided to take the Newton meter or the kilogram meter squared per second squared and give it a special name, which is the joule, symbolized by a capital J. So the joule is the SI unit of energy. It is a metric unit, so you can use metric prefixes with it. So a millijoule would be 1/1000th of a joule, or a kilojoule would be 1,000 joules. A megajoule would be 1,000,000 joules. Energy in the metric system can also be measured in calories, but calorie is not an SI unit. A calorie, though, I'll go into some little detail on this. 1 calorie with a small c is the amount of energy it takes to raise the temperature of 1 milliliter of water by 1 degree Celsius. Okay, and that is a calorie. That's something that you can relate to. You know, it's easy to remember and to kind of have an appreciation for how big that unit is. Unfortunately, it doesn't work with other, it doesn't work with SI units. The calculations don't come out right. So they devised the joule, and as it turns out, 1 calorie is equal to 4.184 joules. Or in other words, a joule is about a quarter of a calorie. So a joule would be the amount of energy required to raise 1 milliliter of water by a quarter of a degree Celsius, more or less. That also means that the joule is a very small unit. And so it is not unusual to encounter numbers that are very large in units of joules. And that's why, for one thing, the kilojoule or kJ is a very commonly used and encountered unit. Now, calories are familiar from food, but actually the calorie with a small c is not a food calorie. The food calorie is a calorie with a capital C. And that is the dietary calorie. And one calorie with a capital C is equal to 1,000 calories with a small c. And the reason they did this is just because using the regular scientific calorie for foods would end up, you'd end up with numbers with you'd end up with huge numbers on the packages. So, a can of Coke that might have 150 calories with a capital C would have 150,000 calories with a small c. So not only would you kind of your eyes pop out when you looked at the label, but also you'd end up taking up a lot of space with all those zeros. So essentially one capital C calorie is equal to 1,000 small c calories or 1 kilocalorie. Okay. So that's just another unit that can be used for energies. Another other unit that can be used for energies. Let's see, did I do everything here? Yeah, okay. Another other unit that can be used for energy, if you really want to, would be in the English system of measurement. Engineers, for some reason, persisted in using English units much longer than other branches of scientists did. And I think it's largely because, at least in the US, most of the stuff engineers had to work on had been built over the years with English units. So they persisted in using English units instead of doing conversions from metric. Anyway, in English units, force units would be pounds, and distance units normally would be in feet. And so we have the foot pound or pound feet. It can be said either way. That can be used as an energy of work or energy. Okay. Work done, let's see, let's look at work done by constant forces and contact forces. If a force is constant in both magnitude and direction, that makes calculations a lot easier, but we can still do them if it changes. The force, and it's easier because if the force is constant in both magnitude and direction, then the force can be factored out of the integral. So if we have the work between points A and B would be the integral of from B down to A of force times dr, we can rewrite that as force times the integral from A to B of dr. And that equals just the force times the position at B, or the displacement at B rather, minus the displacement at A. Or in other words, the magnitude of the force times the magnitude of the displacement times cosine theta. And that becomes a little bit easier to calculate. You can do it in Cartesian coordinates too, if you want to, where the force times the integral of dr just becomes the integral from A to B of the force of the x component of the force times dx. That would be the displacement in the x direction, plus the y component of the force times dy. That would be the y component of the displacement, plus the y component of the force times, or sorry, the z component of the force times the z component of the displacement. And that is just another way of saying fx times the integral of dx plus fy times the integral of dy plus fz times the integral of dz. And that is just another way of saying, well, the integral of dz, or sorry, the integral of dx would be x, but it would be x from b down to a. So in other words, fx times the integral from a to b of dx would be fx times x at point B minus x at point A. So that's essentially what this is here. Plus the same in terms of y, plus the same in terms of z. And x, y, and z are just another way of denoting the position. And so you can write this again as the force, that is the force vector times the displacement at B minus the displacement at A. And that is actually the same as what we had above. And from there, you can go to here, which is what we had above also. So for example, if you have a person pushing on the handle of a lawnmower and the handle makes an angle of theta with the ground, there's a figure in the textbook on page 330 that you can have a look at. That's probably a little more sophisticated than what I can draw. But anyway, work is equal to force times distance, or displacement, if you prefer. And that is equal to the magnitude of the force times the magnitude of the displacement times the cosine of the angle. And the cosine of the angle is because if you look at the force being exerted on the handle of the lawnmower, that would also be theta. The force is being exerted on the handle of the lawnmower at an angle. It's not being exerted horizontally. And the angle is theta. It could be taken as the angle above the horizontal, like here, or the angle below the horizontal at the top of the handle, because the horizontal is going to be parallel to itself, no matter where you draw the horizontal line. So by the rules of geometry, this angle here should be the same as this angle here. And so it doesn't matter which one you call theta. But anyway, the x component of the force would be F cosine theta. And so there you have F cosine theta is the x component of the force, and then d is just the displacement of the lawnmower as it moves forward. Okay. Actually, now let me see. Yeah, this is actually, I think I'll break here because we only have the one chapter left to do over the course of 3 lectures. So I'll try not to present too much all at once. So I think I'm going to call this segment a little earlier than I usually have, and then we'll go on to the second one in just a moment.